solved, means I solved those MCQs and the shared link with you, that in that document it contains the solved MCQs. We will also discuss means how those are solved, and means before that, if you have to refer all those things, we'll go for that. For now, today we will go for our unit 7. We'll start with so contents of this unit are Polish expressions and their compilation, groups, and group codes. It contains 3 subsections. In that, first is Polish expressions and their compilation. Okay, so you will tell me what is Polish expression. Okay, so I have gone through this in DS also, and in second unit of DMS we have seen what are the Polish expressions, not their compilation, but what are those that we have seen already. So you can explain me what is a Polish expression. Okay. Yes. What is a Polish expression? Nobody knows what is a Polish expression? Let it be. We'll see what it is. Polish expressions and their compilation. The expression for adding the numbers 1 and 2 is written in Polish notation as plus 1, 2. Okay. And it is called as prefix form rather than as 1 plus 2 in fixed form. Okay. If 1 plus 2 is there, it is an infix form. But what we in Polish notation, how we write it, like plus 1, 2 means whatever the operator is there, that is given at the first place, and then the 2 operands are given there. Okay. Then in more complex expressions, the operators still precede their operands, but the operands may themselves be expressions, including again operators and their operands. For instance, the expression that would be written in conventional infix notation as 5 minus 6 multiplied by 7 can be written in Polish notation as the multiplication sign, then in bracket minus 5, 6, and then 7. Okay, means which operation we are going to perform first. First, there will be 5 minus 6, minus 1 will be the answer for that, and that minus 1 into 7. Like that, like this, the operation will be here. Why? Because this 5 minus 6 is given in the bracket. Okay. First, the bracket is to be solved, and then this multiplication, that is outside operation, will be performed. If many brackets are there, more than one brackets are there, then what is the case is we are going to solve inner bracket first. Okay, we are going to solve inner bracket first. This is about the Polish notation. Assuming a given arity of all involved operators, any well-formed prefix representation thereof is unambiguous and brackets within the prefix expression are unnecessary. Assuming a given arity of all involved operators, arity means here order of all involved operators, any well-formed prefix representation thereof is unambiguous. For unambiguity, what we have to do is putting the brackets. Okay, there it will be less. It will be doing less confusion. Okay, and it will be unambiguous. And brackets within the prefix expression are unnecessary. Okay, putting the brackets help us to perform the operations, but sometimes in case of Polish notations, it is not necessary to put the bracket. What this sentence is telling us, whatever the inner operation will be there, that will be performed first. It is the logic behind the Polish notation. In case of infix, what we have to do is we have to put the brackets, but in case of Polish notation or prefix, it is not needed. Then brackets within the prefix expression are unnecessary. As such, the above expression can be further simplified to multiplied by multiplication sign, minus sign, 5, 6, 7. So what it will do first, here subtraction of 5 and 6, and then multiplication of answer of this subtraction and 7. Okay, it is the case. The processing of the product is deferred until its two operands are available, that is 5 minus 6 and 7. Okay, two operands are there for multiplication sign. Yes or no? Multiplication sign is having two operands. First is 5 minus 6 and second is 7. As with any notation, the innermost expressions are evaluated first, but in Polish notations, this innermostness can be conveyed by sequence of operators and operands rather than bracketing. Rather than bracketing, what here is used is sequencing of all these operators and operands. Okay, means here we are going to perform subtraction first. So it is fixed that subtraction is to be performed for 5 and 6 only. Okay, not for 5 and 7. Only subtraction of 5 and 6 will be there. There also 5 will not be subtracted from 6. It is the case that 6 is subtracted from 5. Okay, means 5 minus 6. It will be the operation, not 6 minus 5. Here, order of these operators and operands is very important. Okay. Then, in the conventional infix notation, parentheses are required to override the standard precedence rule. Since, referring to the above example, moving them 5 minus 6 into 7 or removing them 5 minus 6 into 7 changes the meaning of the result of the expression. The version is written in Polish notation as minus 5 into 6, 7. Okay, which one? This one. 5 minus 6 into 7. 6 is there in the bracket. So what it will be? Minus 5 will be there. Then first operand, that is 5, then the bracket 6 into 7, how it will be written? Into, that is multiplication sign, 6 and 7. Okay, it is going to change the meaning or change the result. What it will be? Minus 5 in 5 minus here, 5 minus 42. Okay, it will be the answer minus 37. Okay, means answer is differing as we are changing the negative sign, that is subtraction sign. Okay, when dealing with non-commutative operations like division or subtraction, non-commutative operations means again in addition and multiplication we can do 1 plus 2 is equal to 2 plus 1, or 3 into 4 is equal to 4 into 3, but that is not in case of division or subtraction. Okay, 4 divided by 3 is different and 3 divided by 4 is different. Same, 3 minus 4 is minus 1 and 4 minus 3 is only positive 1, means here it is changing the result. So non-commutative operations are division and subtraction, but commutative operations necessary to coordinate the sequential arrangement of the operand with the definition of how the operator takes its argument, that is from left right. Okay, from left to right, how the operations are given, that we are going to evaluate first. Here also what we did, yes, what we did here, first we perform the multiplication as it is the inner one. Okay, and then the subtraction will be there. Yes, for example, divided by sign 10 and 5. With 10 left to the meaning of 10 divided by 5. Read how we read it as divide 10 by 5. Divide 10 by 5, or minus 7, 6. Minus 7, 6. With 7 left to 6 has the meaning of 7 minus 6. Okay, how do we read it? Like subtract 7, subtract from 7 the operand 6. From 7, 6 we have to subtract it. Okay, the polished notation uniquely indicates which operator to evaluate first. It uniquely indicates which operator to evaluate first. A valid prefix expression always starts with an operator and ends with an operand. A valid prefix expression always starts with an operator. We can see here. It starts always from a ends with operand. Okay, then evaluation can either proceed from left to right or in the opposite direction. Okay, in the opposite direction also it can be processed, but generally we go through like this: minus 5 into 6, 7. Operand is at the first place, and we evaluate it from this minus sign to 7 in this direction, from left to right. Okay. For compilation, stack data structure is used. For compilation, stack is used. Now, how the compilation process is, we can see here. Initialize stack as the very first step. Initialize the stack. Then, for each element in expression, 3 steps are there that we are going to do now. If current element is an operator plus or star, whatever it will be, whatever the operator will be there, we have to insert it to the stack. Okay. Then what the next step is? Else it will be a number. If top of stack is an operator, insert this number to stack. Okay. What is there? Whatever the operator was there, that we inserted to stack. Then in the next step, what is there? If operator is not there, in the next step to put number. Okay. If top of stack is an operator, insert this number to stack. Okay. We have to insert this number also to the stack. Then else top of stack will be a number. Okay. If top of stack is a number, then pop it. Now pop again from stack, it will be an operator. Okay. First the operator is means operator is inserted, then whatever the number was there, that inserted. Now what we have to do is, if top of stack is number, then we have to pop that number, and then in the next step what we have to do is pop that operator also. Now with the help of that operator, the 2 operands are evaluated, which is one is in the expression, one is that we have popped. Okay. And the operator that is also popped for performing the operation between 2 operands. Okay. Then use it and evaluate the B and the element. For plus, do B plus element. For star, do B star element. Okay. Give me just a minute. Now we will solve it with the help of whiteboard. Take suppose the example taken is same. 5 minus 6, that is given in the bracket. Multiplied by 7. Okay. What the Polish notation for this is? Multiplication sign, then minus, then 5 and 7. Okay. It is the expression that we have to evaluate with the help of stack. Okay. Now okay. Suppose this is a stack. Okay. I'm trying to draw with the help of mouse. So This is the stack. Okay. Now, what the first uh, here? What the first is? Multiplication sign. Okay. X. Sorry, it is multiplication sign. Then it is a operator, so we inserted. Then pointer shifts to this second element. What this is? It is the minus sign. That also we have to push here in the stack. Okay. Now, what is next? Then it will again check the top of the stack. It is the operator. Okay. Then it is again what it will do? It will insert this 5 to top of stack again. It is a 5. Okay. Then pointer will point to next this one, this 6. Okay. Then what about this 6? Okay. By using eraser, all things. Oh God. Erase. This is our expression. We are up to 6 now. What it will do? Then pointer is at 6 here. Okay. Then it will check what is top of stack. Top of stack is the number. So what we have to do is, if top of stack is number, then we have to pop this 5 here. Okay. Hitting. Then again we have to pop this minus sign also. It will be here. Then it will take this 6. And then whatever the answer will be there, what the answer of this is? Minus 1. Okay. That result of this will be, now top of stack is this one. Okay. Because we have popped this 5 also. Then this minus sign also, means in second step, how the stack will look like? Okay, in second step, it will look like, after popping the 5, this will be the stack. Then what will be there in the next step? It will only have the multiplication sign. Okay. Then next what it will do is, it will store this result again to the stack. Means it will push this result, that is minus 1, to the stack. Okay. Then the pointer will be at this 7 in the expression. Then this, what it will check now? Again the top of stack is number, and this is also the number. So what we have to do is, we have to perform again the operation. So first what it will do is, it will again pop this minus 1. then again it will pop this multiplication sign, and then it will take this 7 here for the operation. Okay, means what the operation remains is -1 into 7, that is -7. Okay, and at the end the top stack will be empty stack. Okay, stack will be empty, no any element will be there in this stack. Getting the compilation process, whatever there was in the wording we saw in the slide that I have performed here with the help of whiteboard. All of you get this compilation process?
Yes, ma'am.
Okay. Nothing is very hard there. Quite easier one. If you know the stacks well, here, whatever the operation is there, that will be performed. Now use this evaluated value as element and go to set. Means the second operation we have to perform, then again we have to perform all this process. And then it's my mistake. Stack is not empty at the last. Whatever the result will be there, that will be stored in the stack. So stack size will be 1. Okay, stack will not be empty. I got confused there. Whatever the result of that expression will be there, that will be stored in the stack, and that will be that top of stack, and stack size will be 1. Okay, keep it in your mind. Simple process is there, compilation process. We have seen that with the help of example. Okay, now the next bit we are going to see is the groups. Okay, in the last unit we have seen what are the algebraic systems. Algebraic systems are all these, means monoids are there, semigroups are there, groups are there, lattices are there. Okay, different types of algebraic systems that we are going to see. In the previous chapter already we have seen is the semigroups and monoids. Okay, what were the properties of semigroups? Algebraic system is what? It is the set of elements with the binary operation such that binary operation is closed there with that set. What is meaning of closed operation there then? If we take any two elements from that set and perform that particular binary operation on those two elements, the answer of that operation will come, whatever that answer will there in the same set only. Okay, that is the algebraic system, and that is called as closed operation. For being an algebraic system, closed operation is the necessity there, means it is necessary that closed by that algebraic system should be closed under the binary operation. Then and then only it is called as an algebraic system. Then we saw semigroups. What is there in semigroups? one property gets added. Okay, associativity gets added in the semigroup, means closed operation and associativity. If these two properties are hold good, then those are the semigroups. Those sets are called as semigroups. Those algebraic systems are called as semigroups. Then in the monoids, what was it? In monoids, one more property got added. For closed operation, associativity, and third one was identity. Okay, identity means what again? It is having one unique element such that the operation performed with that element to any element, any other element of that set, it is giving us the answer that same element. Okay, and that is also closed. So for example, we take it as multiplication operation of the whole numbers, that is 1, 2, 3, 4 integers, we can say. In that case, 1, 2, 3, 4 are there, and operation is the multiplication. And for multiplication, one is the element such that any other element that is multiplied by 1 is that element only, means 2 into 1 is 2, 3 into 1 is 3, 4 into 1 is 4, 5 into 1 is 5. Like that, 1 is the identity element in that set of integers, and the binary operation performed there is the multiplication. Okay, that is nothing but the identity property. Okay, and that was the monoid. Now in groups, one more property is added, and that property is nothing but every element in G has inverse in G. Okay, has inverse in G. Okay, now we have to take the real number set now. Okay, while taking an example, real number sets we will take, or rational numbers also we can take. Means for example, and that should be for every element. Okay, that should be for every element. If I take the two elements, like one, if I take the element 1, then 1 by 1 is the inverse of that 1. Okay, that is nothing but 1. Or if we take number 3, inverse of that number 3 is 1 by 3, and that is there in the real number sets. So real number sets is the group. Okay, real number sets is a group under operation multiplication or addition. Okay, we will see the example, then you will get the idea. What is here in the description of group? An algebraic system G star is said to be a group if following conditions are satisfied. This one we already discussed. Star is a closed operation. Star is an associative operation. There is an identity in G. Identity element will be there, and every element in G has inverse in G. Every element in G has inverse in G. All the elements will have inverse, their inverse in that G. Okay, this is the added property for the group, inverse property. Okay, abelian group. Now what is abelian group? Abelian group or commutative group. Now what is commutativity again? A group G star is said to be abelian or commutative if A star B is equal to B star A. Abelian means what? Again, if it possesses the commutative property, then it will be A star B is equal to B star A. Okay, but my observation, what it is, if the operation is associative, then it will be commutative. Okay, for most of the times, if the operation is associative, then it will be commutative too. Okay, and the name of that group will be abelian group. What it will be? Abelian group. While solving the MCQs, such type of questions may be there. Okay. What is the example given here? We can see in a group G star, the following properties hold good. Okay. What are those? Already we have seen. Here it gets repeated. Identity element is unique. Yes. Inverse of an element is unique. Yes. Any element that is unique, and inverse of that element will also be unique. Means 1 by 2 is inverse of 2. It is not inverse of any other element. For 4, it is 1 by 4 inverse. Okay. For 2, the inverse is 1 by 2. Like that. For 3, it is 1 by 3. These are the inverse of those elements, and those are unique one. Okay. Those are unique one. Then what the next is? Cancellation laws hold good. Now what is cancellation law? We will see here. A star B is equal to A star C. Okay. If this is the case, then what we can see is we can cancel this A, because A is the same for both these sides. And what it will take it as? B is equal to C. B is equal to C. It is known as left cancellation law. It is known as left cancellation law. Now what is there in the right cancellation law? A star C is equal to B star C. So it will be A equal to B. Okay. It will be the right cancellation law. Why it is right? Because the operand which is at the right side, that is getting cancelled. So here it is right cancellation law. Same case here, the operand on the this side, that is left hand side, then this will be A will get cancelled, and what we can write it like is B equal to C. So this will be known as the left cancellation law. And if the operand at right is getting cancelled, then what we can write is it is right cancellation law, because C is cancelled here. What only remains is A equal to B. Okay, A equal to B here. Then A star B inverse is equal to B inverse star A inverse. Okay, this is again the speciality or property of this group. Inverse are there in the group. Okay, so if we have to evaluate inverse for the two elements, that is A and B, how it will be? A star B inverse raised to -1 is there, means inverse. If A star B inverse is there, it is equal to B inverse and star A inverse. Star is what? Any binary operation. Okay, star is what? Any binary operation under which the group is defined. How it will be? A star B inverse is equal to B inverse star A inverse. Okay, B inverse star A inverse is whatever the elements we have taken here. A star B inverse, then what we can write is B inverse star A inverse. Okay, both are equal one. Both the sides are equal. In a group, the identity element is its own inverse. Okay. In a group, the identity element is its own inverse. This also is the property that hold good for the groups. If any identity element is there, if means in a group it is must that there should be an identity element, and for inverse of that identity element, what we have to consider is inverse of that identity element is its own inverse. Okay, is its own inverse. For multiplication operation, as we have seen, one is the identity element, and that one is having only one inverse. Okay, one is having only one inverse, and that is that element only, means one by one it is giving us one. So what is the most important again here in the group? The identity element is its own inverse. Okay, then what is the order of a group? The number of elements in a group are called as order of the group. Okay, number of the elements in the group. Then finite group. If the order of group G is finite, then G is called a finite group. Okay, it is finite group if the order of a group G is finite, then G is called a finite group. Okay, G is order of that group G is finite. That group means again number of elements. Okay, if number of elements are countable in the group, group will be called as finite group. Now here some examples or some theorems are given as the examples. Okay, we'll see those theorems. Total 10 theorems are there, and they can means come in the exam in the form of MCQs also. So if we solve this, we will be able to solve this in the MCQs also. It will clear our group concept also. Show that set of all non-zero real numbers is a group with respect to multiplication. Okay. If we have to show a particular set as a group, we have to again see there for the four properties: closure, associativity, then identity, and then inverse. Okay. So what is that? Set of all non-zero real numbers. Okay, non-zero real numbers means what it will contain. Here, how we are going for this one is here. R star is set of all non-zero real numbers. Let A, B, C are any three elements of R star. Okay, here we have taken R star as set of all non-zero real numbers. In that, zero is not there. Negative numbers are also there and positive numbers are also there. How we are going to take the closure property here? It is, we know that product of two non-zero real numbers. Again, here we have taken the operation as multiplication. Okay, so here product term comes here. What is, we know that product of two non-zero real numbers is again a non-zero real number. Yes, it is there. It is means multiplication of non-zero real numbers is again a non-zero real number. Yes or no? 0 is not there in the set. So we can take any two elements and answer of that two elements is there in that set only. That is A multiplied B multiplied by B, that is A dot B belongs to R star for all A, B belong to R star. Okay. Then what about associativity? We know that multiplication of real numbers is associative. That is A dot B dot C is equal to A dot B dot C for all A, B, C belong to R star. Okay. Means for multiplication we can change the order of the elements. Okay. These are the commutative too. So A dot B first performed, then with dot C is equal to, first here we can solve B dot C, and then answer of that B dot C is A. Okay. Then the next is identity. We have 1 belongs to R star and A dot 1 equal to A for all A belongs to R star. Okay, for all A belong to R star. So identity element exists and 1 is the identity element. Okay, identity element exists set R star with respect to multiplication, because we know any element multiplied by 1 gives that element only. So here in this group R star, 1 is the identity element. Okay, and it exists in that set only. Then the last property, inverse. Okay, last property we can give it as a inverse property. So each A belong to R star, we have 1 by A belongs to R star. Okay, now the set of real numbers also includes decimal numbers or rational numbers. Yes or no? Real numbers means decimal numbers are also there. So for each A belongs to R star, we have 1 by A belongs to R star. Inverse of all the elements are there in that set only, such that A into 1 upon A is equal to 1. Okay, means what we have done here, element A is multiplied by its inverse. Okay, A is multiplied by its inverse and giving the answer 1, where 1 is the identity element. Okay, 1 is the identity element. That is, each element in R star has an inverse. Okay, each element in R star has an inverse, because if we take any number from this R star, suppose 50, then 1 by 50 is also there in the set. Okay, inverse 1 by 50 is the inverse of that any element 50. Okay, which belong to that R star. Okay, then so all the properties are getting here inverse, all the elements in the that whatever group are having their own inverse, and the operation performed with element and its inverse will give us the identity element. Therefore this inverse property get also satisfied here. Okay, so it is a group, that what we can call it as, it is a group. We have proved that set of all non-zero real numbers is a group. Okay. Then second question is, show that set of all real numbers R is not a group with respect to multiplication. Okay. Again, the operation is multiplication, but the set is different this time. Set of real numbers is second. Means what? Here it is included 0. Okay. In the first case that we saw, it was a non-zero real number. Okay. It was a non-zero real number. Here it is said only the real numbers, and in R, 0 also comes. Okay. 0 is the real number. That's why it comes. Okay. Then what the solution is? We have zero belongs to R. As I said, real numbers are R star. What we take it as non-zero real numbers, but in real number set, R is there. Okay. So what we R is there means 0 is there. Okay. So which property get disturbed if 0 is there? Then the first is the inverse, that is the multiplicative inverse of 0 does not exist. Okay. Inverse of 0 will be 1 by 0 and it is infinity. So inverse of 0 does not exist. Hence R is not a group. In the first case, we proved that it is a group, but in the second case it is not the group. Why? Because it is including the 0 in the set. Okay. Now, in previous example, commutativity is also there. If commutativity is there, then that set will be known as abelian group. Okay. Here we know that multiplication of real numbers is commutative. That is A dot B is equal to B dot A for all A, B belong to R star. Here R star is an abelian group. Okay. R star is an abelian group. In the first, we have shown that it is a group and it is an abelian group due to commutativity. And then this one also we have solved. Set of real numbers is not a group because it includes 0 and inverse of 0 does not exist. Then let Z star, the next example or next theorem that we are going to see is this one. Let Z star be an algebraic structure. Okay. Z star be an algebraic structure where Z is the set of integers and the operation star is defined by n star m is equal to maximum of nm. Okay. Maximum of nm. Show that Z star is a semi-group. Okay. Is Z star a monoid? Justify your answer. What we have to prove here is Z star is a semi-group. Semi-group means what? Again, two properties. First one is the closure and second one is the yes. Yes, second one is the which property for a semi-group? Can anybody recall? First is the closure property and second one is the associativity. Okay. Then first what we have to do is we have to check for the two properties, closure and associativity. And then if we have to check it for monoid, if identity property gets satisfied there or not. For associativity, for closure property, what is there? A, B, C are any three integers, then now A star B is equal to maximum of AB belongs to Z for all AB belongs to Z. Okay. Here then closure property. A star B is equal to maximum of AB. Okay. Maximum of AB. Whatever the maximum element will be there, either A or B, that is there in that closure, that is in that set only. So closure property gets satisfied there. Okay. Then for associativity, A star B star C is equal to maximum of A B C is equal to A star B star C belongs to Z star. Okay. So this group is a semi group also. Means whatever will be the sequence. Okay. It is not going to affect. Means first if we take a maximum of A and B. Okay. And then again we compare whatever the maximum of A and B is there and C. Then it is same like maximum of A, B, C. Or here it is equal to, if we take maximum of B and C at the first, and then we again consider maximum of A star and B star C, then what it will be? Yes, same maximum of A, B, C. Okay, so it belongs to Z plus. So the given group is a semi group. Okay, the given group is the semi group. Then for identity, what is there? There is no integer x such that A star x is equal to maximum of A comma x for all A belongs to Z. Okay. So the identity element does not exist, means Z star is not a monoid. Okay. Is not a monoid with respect to this operation, that is maximum of n comma m, because it is not going to satisfy the identity property. Means if we take this one, A star x, then what the operation will be? Maximum of A comma x, which is equal to A for all A belongs to A. But it is not always the case. Okay, A will not be greater at all the times. It might be smaller one also. So what we have defined is that Z star given is not the monoid. Okay, it is only the semi group. It is not a monoid. Are you getting the example? Yes. Have you got this example
Yes.
of semi group? Okay. Then the next example is show that the set of all positive rational numbers forms an abelian group under the composition star defined by A star B is equal to AB by 2. AB by 2 given here is the multiplication of AB, and that multiplication will be divided by 2 again. Then what does set taken is set of all positive rational numbers. Okay, set of all positive rational numbers means 1, 2, 3. Not only the integers, the rational numbers are also there. Means decimal numbers will also be there. Okay. Sorry, just a minute. In case of rational numbers are whole numbers only. All positive rational numbers means again 1, 2, 3, 4 like that. Okay. Here, what the solution taken is a set of all positive rational numbers. Let A, B, C be any three elements of A. Okay. Then we will first go for the closure property. We know that product of two positive rational numbers is again a rational number, that is A star B belongs to A for all A, B belongs to A. Here, after performing this operation on set of all positive rational numbers is also the positive rational number. Okay, so here what what is there? A star B belongs to A for all A, B belongs to A. Okay, whatever the two numbers are there, then the multiplication of those two numbers is divided by 2 is the operation. Okay, so here we have proved closure property for that purpose. Okay, then in communication, what is there? Here in associativity, sorry, what is there? A star B star C is equal to AB by 2 star C is equal to ABC by 4. Okay, it is equal to ABC by 4. Now what is there? If we took this one, A star B star C, it is equal to A star BC by 2. Okay, is equal to ABC by 4. It is equal to ABC by 4. So we can say that these two are the associative equations. Means A star B star C is equal to A star B star C. Okay. Then the third property is identity. What is there in identity? Let E be the identity element. We have A star E is equal to AE by 2. Okay. AE by 2. By the definition of star again, A star E is equal to A. Okay. A star E is equal to A. Since E is the identity from 1 and 2, what we can write is AE by 2 is equal to A. Here AE by 2, because this operation given is AB by 2 when A star B is the operation. We have to perform there is A star E and it is means multiplication of A and E, and that is divided by 2. Okay, then what we have is, by the definition of star again, A star E is equal to A. Means what again? We know any element perform the operation with the help of, or perform the operation with identity element gives that identity element only. Okay, so from this what we have concluded is, since E is the identity from 1 and 2, AE by 2 is equal to A. Here we have written that A star E is equal to AE by 2, and here A star is equal to A. So what we can take is these two RHS, then it becomes as AE by 2 is equal to A. So what will be there? E equal to 2 and 2 belongs to A. Okay, it is like this one. AE by 2 is equal to A. So after cancelling this A from both the sides, what we get it like E equal to 2. That is 2 belongs to A and E, that 2 is the identity element of that set. Okay. What is the identity element of that set is 2. Okay. Because the operation performed here is AB by 2. So identity element exists and 2 is the identity element in A. Now what is there in the inverse? Inverse property, what it will contain is, let A belongs to capital A. Capital A is the set and small a is an element in that set A. So let us suppose B is inverse of A. Okay. What we suppose is B is inverse of A. Means 1 by A is equal to B. Now A star B is equal to AB by 2. That we know by our given operation. Okay. And here B is what? B is inverse of A. Keep it in mind. B is inverse of A. Then again, what we have to have with the definition of inverse equal to 2, means the operation in inverse of that element is giving a element, okay, that is identity element, which is equal to 2. It is by definition of inverse. So from 1 and 2, it follows that AB divided by 2. Okay. Then what we have is the AB by 2 is equal to 2. B is equal to 4 by A, which belongs to A. Okay, which belongs to capital A. That is the set which we have to show in that group. Okay. So after satisfying these 4 properties, that is closure, associativity, identity, and inverse, what we can tell it like A star is a group. We can say that A star is a group. Now what about commutativity? A star B is equal to AB by 2, which is equal to BA by 2, and which is equal to B star A. Okay. B A star B is equal to B star A, because these two are simply the multiplications. Okay. A is multiplied by B or B is multiplied by A. Both are on same. Here we can say for commutativity. Okay, both are giving the same result, whether it will be AB or whether it will be BA, because it is the multiplication. So we can say that it is an abelian group 2. Okay, abelian group. It is the abelian group. Why? Because A star B is equal to B star A. It is not only the group, it is the abelian group, because it also possesses the commutativity. Okay. This one was the example. Then the next example is, in a group G star, prove that identity element is unique. Okay. Now what we have to prove is, in each group that exists, the identity element is unique. how the proof will be given, we can see here. We will take converse of this theorem. Means, do you know the concept of converse? What is to be shown there, or what is to be proved, we take opposite of that. Okay, we take opposite of that and we prove that opposite taken is the wrong. So whatever there given, that is true. Okay, so let E1 and E2 are two identity elements in G. Let E1 and E2 are two identity elements in G. Okay, what we will do now is E1 star E2 is equal to E1. Okay, E1 star E2 is equal to E1. Since E2 is the identity, okay, we know with the help of definition of identity element, whatever the operation performed with identity element to the other element gives the answer that other element. So here we write like E1 star E2 is equal to E1. Okay, same case with this one, E1 star E2 is equal to E2 also. Okay, since E1 is the identity, E1 is identity, so E2 can be given, and as E2 is the identity, E1 will be given here as the answer of this question or answer of this equation. Okay, from 1 and 2 what we have is E1 equal to E2, E1 equal to E2. So what we take it like in a group is unique. Okay, both these numbers we have taken are same, so the identity element is unique. E1 is equal to E2. Okay, so we have proved that identity element in a group is unique. Then the next theorem is in a group G star, prove that inverse of any element is unique. Okay, inverse of any element is unique again. That also we have to prove. How we are going to prove that is, let A, B, C belongs to G and E is the identity in G. Okay, then let us suppose both B and C are inverse elements of A. Okay, means here A is the element and B and C are two inverse of A that we have supposed here. Means 1 by A is equal to B also and 1 by A is equal to C also. Now what we can take it like, now A star B is equal to E and A star C is equal to E also. Since B is inverse of A, we can take it like here identity element. Okay, because B is inverse of A and C is inverse of A. A star B is equal to E, A star C is equal to A. Then from 1 and 2 what we can take it? We have A star B is equal to A star C. Then we know it is like B equal to C by left cancellation law, which we have already seen. B is equal to C. So in a group the inverse of any element is unique. Okay, uniqueness is there in case of inverse also and in case of identity also. Okay, we have proved this one. Then the next theorem is in a group G star. Okay, in a group G star, prove that A star B inverse is equal to B inverse star A inverse for all A B belongs to G. Okay, for all A B belongs to G, what we have to prove is A star B inverse is equal to B inverse star A inverse. What is the proof given here is, consider A star B inverse star A inverse. Okay, star is the operation for the group to be closed under. What first we consider here is A star B inverse star A inverse. Okay. Then what is it equal to? Here first we perform multiplication of A with this bracket. A star B inverse. Okay, what we took it like A star B inverse. Okay, then star A inverse. Okay, then star inverse. How we did like this? By associative property. By associative property, we just what we did, we just moved the brackets. Okay, here one bracket was for A star B and second one was for B inverse star A inverse. Then what we did, we took one whole bracket and inside bracket for this one, B star B inverse. Okay, then B star B inverse is again identity element, that is E, because inverse of this element performed operation with this element is giving us identity element. So A star E star A inverse. Okay, it is by inverse property. Then since E is the identity, it will again come as A star A inverse. Okay, and again we know that A star A inverse is E. It is by again using inverse property. Similarly, we can show that B inverse star A inverse is equal to A star B is equal to E. Okay, here first what we performed is A star B inverse star A inverse. Same case, what we have to show is B inverse star A inverse star A star B is equal to E. Okay, how it will be there? Then A inverse and A will have one bracket, and then instead of A inverse star A, we can write it like E. Then the equation will become B inverse star E star B. Then as E is the identity element, we can take it like B inverse star B, and that is also equal to E, that is identity element. Okay, means hence A star B inverse is equal to B inverse star A inverse. Okay, what we proved here is A star B inverse is equal to B inverse star A inverse. Okay, we can put this formula directly. Okay, while solving any other equation, we can take it directly. Okay, next example is this one. If G star is a group and A belongs to G such that A star A is equal to A. Okay, G star is a group and A belongs to G such that A star A is equal to A. Then show that A equal to E, where E is the identity element. Okay, what is given there? A star A is equal to A. Then since E is the identity element, we can take it like A star A is equal to A star E. Okay, so by cancelling A, we have is A equal to E by left cancellation law. Hence the result follows. What is the result? Identity element is the identity element. What we have to show here is A equal to E. Okay, when A star A is equal to A is there, then that A is nothing but E. Okay, E is again the identity element. Okay. The next example is, if every element of a group is its own inverse, then show that group must be abelian. Okay. G star is the group. Now we know, means it is again possessing all the properties: closure, associativity, identity, and inverse. What we have to show is that this group must be abelian in case that the group, every element of that group is its own inverse. Okay. Let A and B are any two elements of G. Now we know the identity that A star B inverse is equal to B inverse star A inverse. Okay. Here in the last example we have shown this one. We have to consider then this one. A star B inverse is B inverse star A inverse. A star B is again one element from this group G. Its inverse is its own element. Okay, it is A star B. So inverse of B inverse is B and inverse of A inverse is A. So what we got is A star B is equal to B star A. Since each element of G is its own inverse, we can tell it like G is an abelian group, because here A star B is equal to B star A. Then the last example here is, show that G is equal to 1 minus 1 I minus I. I is again the complex number. Is an abelian group under multiplication. Okay, what the operation here is? Multiplication. The composition table of G is here. We have to draw the composition table. Operation here is multiplication. 1 minus 1 I minus I in the rows and 1 minus 1 I minus I in the columns. So 1 multiplied by 1, 1. 1 multiplied by minus 1, minus 1. 1 multiplied by I. 1 multiplied by minus I, minus I. Okay. Now with the minus 1, what it will be there? Minus 1 into 1, minus 1. Minus 1 into minus 1, it's 1. Minus 1 into I, it's minus I. And minus 1 into minus I, it's I. Okay. Then next is I is multiplied by 1. It is giving us I. I is multiplied by minus 1. It is giving us minus I. I is multiplied by I, that is equal to minus 1. Why is it? Because I is multiplied by I square. What the value of I is? Root of minus 1. Okay. And the root of minus 1 square is minus 1. So I into I is minus 1. And I into minus I is 1. Because I square is minus 1. And I into minus I is 1. Got this multiplication, this minus 1 and 1. I is the complex number, yes or no? Which is equal to root of minus 1. Here we are taking square of that root of minus 1. It will give us minus 1. And as it is with negation sign, in this case, it will give us 1. Okay. Then minus I is the last element, that is minus I into 1, that is minus I. Minus I into minus 1, that is I. Then minus I to I, it will give us 1. And same minus I into minus I will give us minus 1. Okay. Because I square concept comes there. So what will be there? By using this table, we will see all these properties. Does it possess closure property? Since all entries in the composition table are elements of the given set, the set G is closed under multiplication. Okay. What the elements are here? 1 minus 1 I minus I. Minus 1 1 minus I. All these elements are there in this set only, that group only. 1 minus 1 I minus I. All these are there. So what we can consider here is closure property. Then associativity. The elements of G are complex numbers, and we know that multiplication of complex number is associative. Multiplication is always associative, so no doubt about associativity. The next is identity. Here 1 is the identity element and 1 belongs to G. Why 1 is the identity element? 1 multiplied by each element of group, it is giving us that element only. So 1 is the identity element. In case of inverse, from composition table, we see that inverse elements of 1 minus 1 I and minus I are 1 minus 1 minus I and I respectively. Okay. In case of inverse of 1, it is 1. Inverse of minus 1, it is minus 1. Inverse of I, it is, yes, inverse of I is minus I, and inverse of minus I is I. Okay. So what we can say is inverse are also there in that set only. Then we consider commutativity. What about this one? The corresponding rows and columns of the table are identical. Therefore, the binary operation multiplication is commutative. Okay. Here, how commutativity means multiplication is commutative. We know that. But what the statement they have given is, see all the rows and columns, those are same. Means first row, first column is same. 1 minus 1 I minus I. Here 1 minus 1 I minus I. Second row minus 1 1 minus I. Second column minus 1 1 minus I. Third row I minus 1 1. I minus 1 1. Fourth row minus I 1 minus 1. Same, the fourth column is minus I 1 minus 1. So what we can take it, this group as, group is possessing commutativity also. So this G, this group is an abelian group. This one 1 minus 1 I minus I, it is the abelian group. Okay. Now one simple concept, group codes is remaining here. So we will see it in the next lecture. Okay, group codes. But after completing group codes, we will again see the MCQs. Those are remain in the last lecture. Okay, in the next lecture, what we will do is, first we will complete this group course and then discuss MCQs. Okay, got it now? And I will share this PPT link in teaching diary. Before studying this group course, go through this YouTube video. It will help us to know what are the group codes. Okay, which is given in this slides only. You can go for that. Okay, so shall we stop here today?
Yes, ma'am.
Okay, so tell me give me the presentee, roll number 1.
Present.
Two. Two. Two is not there. Three.
Present, ma'am.
Four.
Present, ma'am.
Five.
Present, ma'am.
Six.
Present, ma'am.
Seven. Eight. Nine.
Present, ma'am.
10. 10. 11.
Present, ma'am.
12. 13.
Present, ma'am.
14.
Present,
15.
present, ma'am.
Okay. Only 7 and 8 are absent. Okay. We'll meet in the next lecture now. I will end the meeting. Thank you.